We can use relatively simple calculations to convert between pH, the hydronium ion, and hydroxide ion concentrations. So first, let's talk briefly about going between hydronium and hydroxide ion concentrations. We're going to do this based on the equilibrium constant for the dissociation of water. A very small amount of water will dissociate into the hydronium ion and hydroxide ion. This is about 1.0 times 10 to the negative 7 molar of each of these, as we mentioned in the last video. We can write an equilibrium constant expression for this reaction as just the hydronium ion concentration times the hydroxide ion concentration. Remember, water doesn't show up because it is a pure liquid. And this equilibrium constant we give a special notation to of Kw. The W is a subscript, presumably for water. At 25 degrees Celsius, this equilibrium constant has a value of 1.0 times 10 to the negative 14. And we can use that constant to convert back and forth between these two concentrations. So if we solve this equation for the hydronium ion concentration, it will be the Kw over the concentration of hydroxide. And likewise, if we solve it for the hydroxide ion concentration, it looks essentially the same. Just swap the two ions, and the hydronium ion concentration goes in the denominator there, and relatively straightforward. So let's do a couple problems. So in this problem, I'm asked for the hydroxide ion concentration. So my concentration of OH minus will be the Kw over the hydronium ion concentration. And you'll either need to memorize it, or it might be on your exam handout. But the Kw is 1.0 times 10 to the negative 14. Now remember, when we're doing these calculations, it's important that all our concentrations are in units of molarity. This one already is in those units, 3.5 times 10 to the negative 11. I'm going to leave it out here. When we're doing these calculations, strictly speaking, it's divided by an activity coefficient that has units of inverse molarity, and they go away. But when we get our concentration out of this calculation of 2.857 times 10 to the negative 4, we need to put units of molarity on that concentration of hydroxide. Now, this concentration should have two significant figures. Remember, the Kw has two significant figures, and in this case, our other concentration has two also. So rounded to two significant figures, this should be 2.9 times 10 to the negative 4 molar hydroxide. And that's it. Pretty straightforward. One more. What's the concentration of hydronium? So in this case, we're using the equation solving for H+. And Kw over concentration of OH minus. 1.0 times 10 to the negative 14. And we'll just plug our number in here. Our hydroxide ion concentration, the 1.91 times 10 to the negative 5. It's already in units of molarity. And I got 5.236 times 10 to the negative 10 molar. And again, it's going to be two significant figures. This Kw, in this case, is limiting the precision of our answer, or 5.2 times 10 to the negative 10 molar. Now, I want to draw your attention really quickly to an observation about these exponents here. I want you to note that when you add them up, they add up to negative 15. And the exception is that it might be negative 14 with 1.0 times 10 to the something. So if your number in front is exactly 1, you'll get a sum of exponents that's negative 14. But this is a very simple way to check that you haven't made a calculator error in typing your numbers in. Okay. The next set of calculations is converting between pH and the hydrogen ion concentration. And remember, the P function was the negative log, in this case, of the concentration of the hydronium ion. So this equation is relatively simple for calculating pH. If we want to take the inverse of that, if we want to solve for H+, then what we're going to do is move the negative sign and then undo the log by raising it 10 to that power. So 10 to the negative pH is the inverse of the negative logarithm of the concentration of hydronium ion. I want to just throw out a couple calculations here to talk about the way significant figures are handled in logs and exponents. And your instructor may not be picky about this, but just so you know, if I have a pH of 4.26, and it's the negative log of, in this case, it would be 5.5 times 10 to the negative 5. The proper number of significant figures, and I'm going to go ahead and change some colors on you. Is 2 digits after the decimal point in the pH. Oh, geez, what did I say? 2.6. Two significant figures here become 2 digits after the decimal point. These are called the mantissa here, and this is called the ordinate, the one in red. The ordinate describes the exponent. If I do another calculation, maybe it becomes a little easier to see that if I have 11.26 will be the negative log of, again, 5.5 times 10, in this case, to the negative 12. Sorry, wrong color. So in this case, the numbers before the decimal point there describe that exponent, and the numbers after the decimal point relate to the number. So maybe that helps you remember 2 sig figs in the concentration is 2 digits after the decimal point in the pH. So let's do a couple calculations, and I'll use the correct sig figs here. Your instructor may not be as picky. So in this case, pH given a hydronium ion concentration, so that's going to be the relatively simple equation. pH is negative log of the concentration of the hydronium ion. So negative log, and we'll just plug in our concentration. We drop the units. 7.2 times 10 to the negative 3. And the answer here comes out to be 2.14. Two significant figures become 2 digits after the decimal point. The inverse, if we're trying to get the concentration of hydronium ion, that's going to be equal to 10 to the negative pH. So 10 to the negative 11.421. And I punch this in the calculator, I get 3.7931 times 10 to the negative 12. 3 digits after the decimal point there becomes 3 significant figures here, or 3.79 times 10 to the negative 12. And I need to be careful here to put on units of molarity. Now just a quick way to check your work on these. Watch that the exponent the numbers before the decimal point are close to the exponent in your concentration. And that will be an easy way to check. These numbers will be the same if this number is exactly 1. If they're not exactly 1, the exponent in your concentration will be 1 higher than the digits before the decimal point in the pH. The hardest problems in this sort of set of pH calculations are when you have to do both conversions, when you're changing hydroxide to pH or pH to hydroxide. In this case, you can't go there directly in one step, and so we'll do it in two. If we're starting with a hydroxide ion concentration, in order to get to pH, we need to first get the hydronium ion concentration. From the hydroxide ion concentration, we're going to use the equilibrium constant for the dissociation of water. So Kw over concentration of hydroxide, so 1.0 times 10 to the negative 14. And we'll divide it by that 1.06 times 10 to the negative 5 molar. And out of this, we get 9.434 times 10 to the negative 10 molar. Now I'm carrying 2 extra significant figures to avoid rounding errors. Remember, it's 2 sig figs from that 1.0, the Kw. Now that I have a concentration of H+, I can come along and do my pH calculation. My pH is the negative log of the concentration of that hydronium ion, H+. So negative log. And don't type it in your calculator again. Use the answer button. If you don't know how to do that, look it up. But just pull that 9.434 out of memory in your calculator to avoid those rounding errors. And when I punch that number in, I'm going to get 9.0253. Now, even though I started with 3 significant figures, I don't want 3 digits after the decimal point here. When I did this Kw conversion, I lost a significant figure. And so my answer should go to 2 digits after the decimal point, or a pH of 9.03. Okay, going the other way, if I'm starting with a pH and trying to get hydroxide, before I can get hydroxide, I have to first get the concentration of the hydronium ion, which I will get as 10 to the negative pH, or 10 to the negative 7.824. And when I punch this in my calculator, I got 1.4997 times 10 to the negative 8 molar H+. Now, in the pH, there were 3 digits after the decimal point, so my concentration should have 3 significant figures. And again, I'm keeping a couple extra digits, but it's even better if you just leave it in your calculator memory. To get the hydroxide ion concentration, which is what this problem asked for, it's going to be the Kw over that concentration of H+ I just calculated. So 1.0 times 10 to the negative 14 over the 1.4997 times 10 to the negative 8 molar. Well, let's leave the molar off. And this had 3 significant figures, and I get 6.668 times 10 to the negative 7 molar OH minus. And because my Kw has 2 significant figures, I should have 2 significant figures in my answer, so 6.7 times 10 to the negative 7 molar hydroxide. Now just those check your work steps. When I did my pH to H+ conversion, that negative 7, or that 7 became an 8, that's good. And then if I look at my exponents in the Kw conversion, they add up to negative 15. Same thing up here. Negative 5 and negative 10 add up to negative 15, and the negative 10 and the 9 are one number off. So Those are just quick checks you can make to avoid calculator errors or correct calculator errors before you turn in your exam.